Every single computer, whether it's the one in your pocket or a massive supercomputer, plays by a very specific set of rules. But what are those rules? And maybe more importantly, what are their limits? That's what we're going to dig into today. We're going to use a bunch of cool puzzles to explore the very edge of what's even possible in the world of computation.
All right, let's just dive right in with the big one. Are there problems that a computer can never solve? And I don't mean problems that are just too slow or take too long. I'm talking about problems that are fundamentally, provably impossible for any machine, no matter how powerful, now or in the future, to get a guaranteed right answer for. That's the mystery we're setting out to unravel. Okay, so to get our heads around this, we've got to start at the very bottom of the computational ladder. Let's imagine the absolute simplest thinking machine you can think of, one that can spot some basic patterns, but, and this is the key part, has absolutely zero memory. So these really simple machines, they can only understand something called a regular language. And look, when we say language here, we're not talking about Python or Java or anything like that. Nope. In this world, a language is just a collection of text strings, sequences of characters that all follow one specific, really simple, repeatable pattern.
But just how simple are we talking? Well, let's try a puzzle. This one's straight from our source material. Imagine you've got a string of ones and zeros. Your challenge is to come up with a single, simple rule that accepts strings like 11 or 1010, both have an even number of ones, but rejects something like 101. And here's the kicker. Your rule has to work for any string, no matter how long, as long as it has an even number of ones.
And the answer? It's this beautifully simple pattern. It's so elegant. What it's basically saying is this. Look for a chunk of text that can have any number of zeros, then a 1, then maybe some more zeros, and then a second one. See? Each of those chunks has exactly 2 ones. So if you just allow that whole chunk to repeat as many times as you want, you guarantee the total number of ones will always be even. Pretty clever, right?
Now, the little theoretical machine that actually runs these simple rules has a bit of a fancy name, a deterministic finite automata, or a DFA for short. Yeah, I know, it's a mouthful, but the idea behind it is actually super simple. It just has a handful of states, like on or off, and as it reads a string of characters, it just hops from one state to another. Its entire knowledge of the world is just, what state am I in right now? That's it.
You know what a DFA is like? It's basically a vending machine. Think about it. You put in a coin, clunk, it changes state. You press a button for your snack, clunk, it changes state again. It just follows this really rigid path based on what you do. It has no idea you put a coin in 3 steps ago. All it knows is its current state. That's a DFA.
Okay, but this whole no memory thing, it's got some serious limits. I mean, simple pattern matching is great and all, but it breaks down pretty fast. What happens when a problem needs you to remember something, even just a little bit? Well, for that, we're going to have to upgrade our machine. It's time to give it a little bit of memory. So, how do we do that? Well, let's look at the next rung on our ladder. Our first machine, the DFA, had 0 memory. The next step up is something called a pushdown automaton, and its upgrade is a simple stack. Now, a stack is exactly what it sounds like. It's a last-in, first-out kind of memory. It's like a stack of plates at a buffet. You can only put a new plate on top, and you can only take the top plate off. So why on earth do we need this stack? Well, let's take a look at a slightly trickier problem also from our source quiz. How could a machine check if a string has the exact same number of zeros as it does ones? A DFA, well, it just can't do it. It has no way to remember. It might be able to count 1 or 2, sure, but it can't remember, say, 100 zeros to make sure there are 100 ones later on. It just doesn't have the memory for that.
Here's the problem in a nutshell. Look at this first language, L1. It's just a bunch of zeros followed by a bunch of ones. Any number of each. A simple DFA can totally handle that. No problem. But now look at L2. This one requires the number of zeros to equal the number of ones. And to do that, you have to count them and remember the count. And that, right there, is where our little DFA just throws its hands up and says, I can't do it.
So what's the hero of this story? It's the pushdown automaton, the PDA. And really, all it is a DFA with that stack memory we talked about bolted on. That stack gives it the superpower to recognize a whole new, more complex class of patterns, which are called context-free languages. And you've actually seen this in action, I guarantee it. A perfect example is how a code editor checks if your parentheses are balanced. Every time it sees an opening bracket, it pushes it onto its stack. When it finds a closing bracket, it pops the matching one off. If the stack is totally empty by the end of your code, you're golden. Everything is balanced. That is a PDA doing its job. right there in your text editor.
Okay, so we've gone from no memory at all to a simple stack. But let's be real, that's still not powerful enough to describe the computer on your desk. We've climbed from the ground floor to the first step of the ladder, but now it's time to jump to the top. We need to look at the theoretical blueprint for basically all of modern computation.
And this is the Turing machine. As a concept, it's incredibly simple. Just imagine a little machine head that can read, write, and move back and forth along an infinitely long strip of tape. That's it. But, and this is the mind-blowing part, that simple model is so ridiculously powerful that it can be programmed to simulate any algorithm that could ever be run on any physical computer. It is the universal model of computation.
And this is where the Turing machine just flexes its muscles. It can handle everything we've seen so far. Those simple patterns a DFA can do, easy. The counting problems that a PDA can handle, no sweat. And so much more. This, right here, is the absolute peak of our computational ladder.
So, we've made it. We're at the top. We have this all-powerful universal machine that can simulate any algorithm we can dream up. It seems completely unstoppable, right? It feels like we finally found a machine that can solve anything. But this is where we hit the most profound, the most shocking twist in the entire history of computer science.
And that brings us to the ultimate question. If a Turing machine can run any algorithm, does that mean it can solve any problem? Can we write an algorithm for literally every question we could ever think to ask? Well, the answer, which was proven all the way back in the 1930s, is a shocking, definitive no.
This is where we have to talk about a concept called decidability. It's a huge idea. A problem is considered decidable if you can write an algorithm, a program for a Turing machine, that is guaranteed to eventually stop and give you a correct yes or no answer for every single possible input you could ever throw at it. And this idea, it basically splits the entire universe of computation in two. On one side, you have decidable problems, where an algorithm that always works is at least possible. But on the other side, you have undecidable problems. And for these, it has been mathematically proven that no algorithm can ever be written that's guaranteed to give a correct yes-no answer for all inputs. It's just not possible. The most famous example of this is the halting problem. The impossible challenge of writing one program that can look at any other program and tell you for sure if it's going to run forever in a loop or eventually stop. Now, I know this might all seem super abstract, right? Like some philosopher's game played out on a chalkboard. But understanding these limits isn't just a theoretical exercise. It is the absolute foundation of all modern computer science, and it has some massive real-world implications.
So let's just quickly recap our journey, right? We started at the bottom with the simple patterns of regular languages, which are handled by those memoryless DFAs. Then we added a stack to climb up to context-free languages with PDAs. We hit the peak with the all-powerful Turing machines that can handle any computable language. And then we looked over the edge and discovered that beyond that peak lies this vast, unreachable territory of the uncomputable.
So why does any of this matter? What's the big takeaway? Well, for starters, this theory helps us design better programming languages because it tells us what's even possible to check for, grammatically speaking. It also sets the hard boundaries for fields like artificial intelligence, proving that some questions are just plain unanswerable. And finally, it gives us a way to classify problems by how hard they are so we know which ones are worth trying to solve perfectly and which ones we need to find clever workarounds for.
And so, we have our answer. There are, without a doubt, problems that computers can never, ever solve. These are fundamental limits baked into the universe of logic, and no amount of processing power will ever get us past them. So the final question I want to leave you with is this. Knowing there's a hard limit, a line we can never cross, what does that truly mean for the future of computing and for a quest to build true artificial intelligence?